Rajkumar finished his PhD from Institut Center. Then he moved to visit NISCR, where he spent 6 months, I think, at NISCR, 3 months. He spent 3 months at NISCR Bhubaneswar, and then he went to do his postdoc at Weizmann Institute. He spent 2 years there, and now he is at Institut Curie in Paris. So today he is going to talk about cellular spreading and migration on curved surfaces. Rajkumar is going to be here till tomorrow morning when he is leaving. So any of you who would like to talk to him, he is sitting in this visitors bay at desk number 2. So Rajkumar.
Thanks, Kumar, for the introduction and also hosting me, and thank you all for being here. So, am I audible? Microphone is not open. Mic not open.
Sorry.
Okay, so it's working now.
তুমি না এদিকে ফিরে দেবে তো মাইক্রোফোনটা এদিকে লাগিয়ে দাও।
Okay, so is it better?
Yes.
Okay. Thanks, Sankalam, for the introduction, and thank you all for being here. And so I'm Rajkumar Sadhu. I'm currently a postdoc at Institut Curie, and the work that I'm going to discuss is done in my previous postdoc with Professor Nirbaugh from Weizmann Institute of Science. That actually deals with the cellular spreading and migration of curved surfaces. So, to motivate the in the whole lifetime of a cell, it has to deal with lots of surfaces that is not very simple. It is highly curved, highly complex geometrically. Few examples are shown here. Inside the body, cell moves or spread. It has to deal with the nearby tissues. It also has to deal with the protrusion of the other cells. One interesting example is, so this is a neuron cell. It is a cylindrical part called axon, and this one cell actually form myelin sheaths. So they form layer by layer, many layers, and it also has to deal with this cylindrical part of the axon. Even outside of the body, there are lots of such examples. For example, this Dictyostelium discoideum cell, it is kind of amoeba cell that lives in soil, and soil in the microscopic range actually it is highly complex geometrically. And throughout its lifetime, the cell has to deal with such a geometrically complex environment. So the motivation is that it is important to understand how a cell spread or migrate when it is exposed to some curved surfaces. However, most of the experiment is actually limited to the cellular spreading and migration on flat surfaces. But there are few experiments that also deals with cell migration, cell spreading on curved surfaces. And I have actually cited some of them that is important here for us. One such example is that these T lymphocyte cells in this paper are studied on sinusoidal patterns. So if you concentrate on one cell, you will see that qualitatively these cells are actually either going along the axis or occasionally they are jumping from one to another minimum, but you will rarely see any cell that is on the top or on the maximum and it is migrating along the axis. So here it is clear that these cells prefer the minimum when they are on the migrating on the axis. On the other hand, if they have to actually go from one minimum to another, they prefer to minimize their time on the maximum. Few other examples are that. So these cells, so the length scale of the substrate is much different. It is of micron size. These wave patterns, sinusoidal patterns are of micron size. On the other hand, here this is the cell, and the fiber, cylindrical fiber, is of the order of few hundred nanometers. Here, these people observe that these leading edges protrusions of the cell, they coil on the fiber, this fiber here also. Now, here also, qualitatively, if we observe, they are not going axially, they are not extending axially, but they prefer to coil. So, in this experiment, we can ask some simple questions. For example, what are the mechanisms that are driving these cells to go along the axis when they are on the minimum and they don't prefer this maximum and they try to cross from one minima to another minima at higher angles. And also in these examples, why rather than extending these leading edges axially, why they prefer to coil? And can a single model explain these two phenomena that looks very different, like one is in micron scale and one is in 200 nanometer scale? So now I'll discuss the model. So the model consists of a vesicle, closed vesicle, that is formed by this kind of triangulated surface. This kind of model is already done much long ago. So the surface is formed by triangles, and in our case, we don't have any intracellular material. So inside of the cell is empty. So actually, I should emphasize that we are not trying to model the full shape of the cell. So this vesicle can often be represented as cell fragment, lamellipodia of the cell, or leading edge of the cell. So this is not the full shape of the cell. Now we consider some kind of curvature sensitive proteins. These red dots also shown here. They sense curvature and also they try to bend the membrane outward. And this happens because of this minimization of the selfish energy. So the energy of this bending energy of this vesicle can be written in this form, where C1, C2 are the principal curvature of the membrane, and C0 is the spontaneous curvature. And that the spontaneous curvature of those locations where there are proteins is positive. This means that these parts will try to actually be positive in order to minimize this energy. So these proteins will try to curve the membrane in the outward. On the other hand, if there are no such protein, then the spontaneous curvature is zero, and this part would like to be flat. We also consider that these proteins have some kind of interactions. So this is the interaction energy due to interaction. So when they are in the nearest neighbor, it will have some energy contribution. If they are not in the nearest neighbor, then they will not have any energy contribution.
The protein is supposed to have a surface.
On the surface, yes. On the surface, on these vertices.
Yeah, no, I'm saying if you look at this
Yes.
cell,
Yes.
the model cell,
Yes.
the proteins lie on the surface of the cell or what? So do they pertain binding to the substrate?
In real case, you are asking?
No, no, I'm saying
Yes.
in the model.
In the model, the surface is like a very thin, there is no width, and they bind on the surface. So we also assume that these proteins recruit actin filaments and that polymerize and apply a force on these proteins. It is very similar to if there are some kind of electric field inside the vesicle, and instead of these proteins, there are charged particles. This electric field will apply some kind of force. We assume that the source of this force is actually due to the actin polymerization, and they are applying a force on those locations where there are proteins because these proteins are recruiting actin filaments. And we actually actually the dynamics of actin is expressed very simple way that they only apply a force and there is no dynamics in the model. So we are not updating actin field or actin polymerization depolymerization. We assume that if the local surface of this normal changes, only the direction of the force will change, and if the force will be always in the normal to the local surface only. And because of this, there are some kind of energy contribution. So if there is a displacement along the direction of the force, it will contribute some negative energy. And the last energy contribution is the addition energy. That is because of the interaction of this vesicle with the substrate. And we represent it in this way. So integration of dA is the adhered area, E addition is the addition strength. So this energy is proportional to the added area. And in our discrete model, this integration of added area is just the number of vertices that are touching the surface. Now we did Monte Carlo simulation. So in Monte Carlo simulation, we actually do some kind of move dynamics, and in that dynamics, we actually calculate the energy change, and that decides whether this dynamics will happen or not. There are two kind of dynamics here. One is the vertex movement, and second one is the bond fluid. So in the vertex movement, we choose a vertex and try to move it to its nearby locations, keeping in my mind that it cannot move to large distance, otherwise it will break the self-awareness of the network. So it can only move to very small distances around this point. This is one dynamic. Second dynamic.
It doesn't have to move along a bond. It can move
No,
in
anyway, in three-dimensional space, it can move to any direction. And the second movement is the bond flip. In this, we have to put two triangles that are having the same bond. This one, we will disconnect this one and it will reconnect between the other two unconnected vertices. And these two dynamics are enough to have give safe fluctuation of the vesicle and also the diffusion of these proteins on the surface of the vesicle. And when also when
explain this, do you have protein on each vertex are only few of them?
few of them.
And even those vertex can move, or those vertex are being down by the force.
So proteins are actually attached to the vertex, and bond flip dynamics gives this vertex a lateral diffusion. If there are many bond flips,
no, one dynamics is bond flip, another dynamics is vertex slides.
Vertex move.
So I'm saying this red dot, vertex which are actually attached to the protein, they can also slide on bond.
Yes. Like oh, let me clarify. So this protein is attached to this vertex always. So if the vertex moves from here to here, protein is also moving. And in the bond flip, the vertex as well as the proteins are diffusing on the surface. And it will become clear when I actually show the movies.
But the protein moves from vertex to vertex.
No, they don't jump. They don't jump. They attach to this vertex.
Okay.
And bond flip dynamics actually make these vertices diffuse on the surface.
The bonds are essentially representing membrane rigidness or something, right? And it's elastic.
So here actually this is
the membrane rigidity, right? Bonds that you're talking
here. Here, this is just the model of the surface. There are rigidity is defined by this bending energy. This is also kind of
membrane. The bonds represent what?
Bond represent what? So,
well, probably you need the bonds to define the surface.
I think it is just to define the
part of the elastic.
Elastic network.
Yeah. That's what that is.
Okay. Yes. So in this case, we don't have elasticity, but what we have is the maximum and minimum limit of this length that define this. Like, yeah, and you are right. So it could also introduce some kind of elasticity depending upon the length of this bond. Yeah. So we'll calculate this energy and we will try to do either a vertex move or a bond flip and check if the energy is negative or positive, and depending upon which we will actually do the dynamics. So the assumption of this curved membrane protein is not arbitrary, and there are a number of evidences that these bar domain proteins have curvature sensitivity. There are also evidences that some kind of curvature sensitive protein like this one, IRSP53, binds with some other kind of protein, and the other protein have property to recruit actins. So they form some kind of complex. That complex has one property of curvature sensitivity and another property of actin recruitment, apart from other functions. So a single red dot in our model represents these kind of protein complexes, and not a single one, but a large patch, because our model is a post-scan model. So a single point doesn't represent a single lipid or a single protein, rather a large patch of such proteins. So this model is quite successful in capturing the features of cell migration and spinning on fat surfaces. So you can see this is moving on a fat substrate, and the shape of this vesicle is very similar to these shapes that is observed in real experiments. Also, there are few features that is seen in real cell. For example, these kind of structures, and also these migrating vesicle often use. So this okay. So there is a cluster of protein that is asymmetric. So in the back side there is no protein. In this side there are proteins, and there is a force in this direction. So we have to choose the protein density in that way. Very large protein density will not make this crystal motile. And these often can break their motility property. And in real cell also, they have this kind of dynamics has been seen, but you can see that they again repolarize. So there are some kind of signaling mechanism in real cell that repolarize, but in our model, this is not there. So once this motile it becomes non-motile, it cannot regain this motility property. So our model could also capture the process of phagocytosis, so which is the process of engulfment of large particles by the cell, and which actually qualitatively show that in the beginning there are at the large actin aggregate that there are actually they are like small cluster of actins which becomes very continuous in the meantime, and at the end this cluster disappears. In the simulation also we see that there are small cluster of proteins because they are coupled with actins. You can say these are the cluster of actins, and they becomes more continuous, and then finally they vanishes after completing the engulfment process. So this model is actually able to capture these nice features, and then we actually decide to actually extend it to more complex systems. So what we did there is that we take a motile vesicle on the that is generated on the flat surface, and we can put it in the flat surface and then curve it. Then we can generate a motile vesicle on a curved surface. Alternatively, we can start with spherical like vesicle, keeping the parameters such that it can form this kind of shapes. We have to choose proper addition, strength, force, density, everything in order to form this. And occasionally you can see that the symmetry is broken. You don't have any kind of specific term to break the symmetry, rather it breaks spontaneously. So in the beginning there are some kind of curved region forms because of the addition. They actually affect more curved protein in order to minimize the energy, and then it promotes more bending, and then more actually curved protein comes. So there is a positive feedback kind of mechanism, and that ultimately gives this kind of symmetry. Now, what will start here is that we take two migrating vesicle. One we put on the minimum of sinusoidal substrate, one on the maximum, and the size of the vesicle is much smaller than the wavelength. And keeping in mind the previous experiment that I showed you in the beginning, lymphocyte experiment, the cells were much smaller size. And if you see the dynamics, and if you remember that movie, these cells were either moving on the minimum or they were crossing from one minimum to another at some high angles, and we did not see any cell that is moving on the maximum in the axial direction. And here also we see that either they move around the axis when they're on the minimum, and when they're on the maximum, they quickly slides down and come to the minimum and settle down there. Now we can understand this because we have all the energies. We can measure this energy and check these energies. So only two energies important here: the addition energy and bending energy. Protein protein binding energy is not important because this cluster size is not changing much. Active energy is only actually allowing it to move as a whole without changing any shape. So these are also not important. So if we measure the addition and bending energy, for this case, this is the addition and this is the bending energy. For this case, this is the addition and this is the bending energy.
The surface doesn't have any dynamic by itself, right? The surface is static.
Surface,
The conjugation also doesn't change.
this substrate.
Yeah.
Yes,
This
this is static and rigid. Yeah, right. And you see that the energy, addition energy and bending energy drops and this line corresponds to the one where, so this is the minimum. So when they cross the minimum or come close to the minimum, the energy actually reduces. So we can say that by actually measuring the energy, we can explain this. There are even more qualitative explanations that will come, but at this stage, we can say that the energy is minimum when they are on the minimum of the substrate. And
No, when you say minimum of the substrate, what do you mean? There's gravity or something?
no gravity.
So how do you decide minimum?
So this is the
symmetric. I mean, how do you distinguish top from bottom? I mean,
yes, that this is distinguished.
How? So, I mean, I can see that only addition and bending. I mean, when you say that minimum of the substrate, I mean, without gravity, how do you show that what is the minimum of the substrate?
Yes, so that will come. Maybe I can explain here also. So these vesicles try to adhere, and maybe it will clear when I will go to the constant curvature. This will explain everything. So it actually distinguishes between concave and convex because
concave and convex.
Yes. Yes. Everything will become clear. I'll come.
No, then you should say that concave and convex, not minimum.
Okay.
Concave and convex. Some field or something.
Okay. So this experiment is done on the BB cells, these amoeba cells, by our collaborators. And what they did is that they capture the center of mass of the cell, many cells, in many time, and they also observe some kind of clustering on the concave part. And in the convex part, there are very few cells. Now, in the previous simulation, we see that they don't cross from one minimum to another because the size of the vesicle is very small, and this vesicle could not fill the other sign of the curvatures. Now, if we make it a little larger, it can also cross from one to the other. And if you do many such experiment simulation and average over this value of this angle at which it crosses from one minima to another, to the direction of migration or force, and the direction of this axis. So this angle will be larger. By larger, we mean it will be towards the pi by 2 and not towards 0. And this is the result that we obtained from the first figures of the lymphocyte cells. And we also see that in this experiment also they try to cross at large angles. Now we will increase the vesicle even a little more larger so that at a single time the cell or the vesicle can also explore other parts. And in this case, you see that there are another kind of mode of migration that after some time it will become fully orthogonal. And these experiments are done on fish keratocytes. These are the fish keratocyte cells. And here also the size of the cell is much larger, very similar to this simulation. And here also we see that there are this kind of migration where they actually go orthogonal to these patterns. Now, why they are doing so? We already saw that it prefers to cross these convex regions by at 90 angle, and the vesicle has some kind of reorientation time. So if it spends more time on the minimum, it will reorient along the axis. But these are very small, and because of this, when it crosses one maxima, it is happy, it tries to reorient, but the reorientation time is much larger than the time that it goes from one maxima to another. So because of which it actually prefers to go in the orthogonal direction at the end. And also these cells are showing this kind of migration. And the speed of the vesicle or the cell both show periodic variations. Unlike these cells where there are lots of noise, in our simulation we can see that there is a nice periodicity if we average over all these periods. On the other hand, here because of the noise, maybe the periodicity of this like velocity is not observed. But
what is it?
so this weight is the height, like I'm averaging from so from here to here.
This axis.
Yes, yes. So this is the, you can say this is this part from this point, and another point after one period is this point, and this is this one minimum. So this is the full period of this sinusoidal pattern, and you see that there is a nice periodicity also in this peak. These experiments are done by these people, and we now go to the constant curvature case. So if the cell is only actually filling the curvature and not on which kind of surface they are, then the behavior that they are actually showing on the top of the sinusoidal should be same as a behavior on the fiber, because it is also convex. And you see that indeed it is showing this kind of behavior. So crossing sinusoidal heights at large angle is very similar to the circumferential motion that it is performing, and it is not stable in the axial direction. And this can also be seen by measuring this addition, bending, and the binding energy between proteins. And energy is minimum. And in next slide, I will also explain qualitatively why it is preferring to actually migrate circumferentially rather than going vertically. Now, when the reticle is on the minimum, it should behave in a similar way when it is on the concave part of the sinusoidal pattern. And indeed, it prefers to go axially. And there are few experiments that also actually we see similar behavior, like these are the BB cells, this kind of cells, and they have some preference to move circumferentially. And if we plot this distribution close to the 90-degree, there is a maximum. So they prefer to rotate circumferentially. And these experiments are done by these people. And another experiment where people did this kind of NDCK cell inside the fiber, they actually see that in the axial direction there are long trajectories, so they prefer this axial migration, very similar to that we observed here. And these experiments are done by these people. And even much better experiment and very similar to our simulation is this experiment that is done on micro pillars. So they are vertical pillars, cylindrical as well as triangular, and these cells are also the GD cells. And what they observe is that these cells very nicely rotate circumferentially. The size of the cell is comparable to the cylinder, that is similar to our simulation. And second observation is that when they rotate on the triangular pattern, they also rotate, but the speed oscillates. So speed oscillates between maximum and minimum, and they observe three equidistant peaks in a full period. There are some kind of noise, but yeah, there are like three equidistant peaks, and these peaks are arising because of this curvature change. They are highly curved part, and we can also verify this kind of observation. So the experiments are done by these people by considering elliptical cylinder. So in the triangular cross section in the previous experiment, they have different curvatures, high curvature, low curvature. If we take a circular cylinder and make it a little flatter, we can also generate a curved part, more curved region, and a less curved region. And when we actually did these simulations and plot the speed of center of mass or the leading edge or the trailing edge, we also see there are two peaks. There, in their experiment, there are three edges. It was triangular. And in our case, there are two peaks because there are two regions that are highly curved. And at the end, I will come to this where we will compare all the cases and try to qualitatively understand why the vesicle is preferring the circumferential direction rather than the axial direction. So in this case, these are the same, just two view. The vesicle is in the axial direction. In this case, the vesicle is in the circumferential direction. So if we see the direction of these forces, so one component will be along this direction that will actually allow it to migrate in this direction. Another component will be these forces that will try to stretch the vesicle. Now, since it is on the curved surface, these forces will be directly in the downward direction, and if they stretch this vesicle, they will also tend to de-adhere it because the surface is curved and the force is straight in the downward direction. So these forces, when it will stretch the vesicle, will also make some of the vertices unadhered. That is not energetically favorable. Now, if they stretch and also try to adhere, then it also has to bend. So we see that in this case, these forces that are acting on the side and try to stretch the vesicle, they are not actually mm, very happy, and they are not trying to minimize all kind of energies here. On the other hand, if you see this orientation, circumferential orientation, again there will be forces on this direction that will tend to stretch the vesicle. Now we check that some of these vertices are unadhered on the leading edge, and when the vesicle stretches, some of these unadhered vertices gets adhered because it stretches and in this direction, and because the direction is the zero curvature direction, it doesn't have to pay much bending energy, and also these edges that are adhered remains adhered even if the vesicle is stretched because it is stretching along this zero curvature direction. So this is happy. The force is able to stretch it, and quantitatively you can show this, like if you measure aspect ratio, that is width by length, this will quantify how much it is getting stretched. So in this circumferential case, in this case, it is highly stretched in comparison to the case when it is axially oriented. And also the adhered area is higher than in this case. So in this case, the forces are able to stretch the vesicle much much larger than this case. They are well adhered, and since it is stretching along the zero curvature direction, bending energy is not also getting larger. So these are happy. In the minimum, in the inside of a cylinder, we see that this actually vesicle is as well adhered as when it is on a flat surface. So it is not feeling anything like it is very, very perfectly adhered. So it is happy, and it is not trying to change its direction, and it is moving along the axis. So this gives a qualitative understanding of why this is preferred rather than this. Now, so far we are dealing with this migration of the surface vesicle. Now we will go to the case where the vesicle will not be a migrating vesicle, rather a simple vesicle, non-migrating, and it will adhere on these cylinders of different radii to fix adhesion strength and force to some values so that it is perfectly adhered, and it also forms this kind of like two arc like shapes. If force is very small, these coiling structures will not be observed. So we first fix force and adhere strength. That is already actually we have some idea from the study of a flat surface. And what we are doing here is we are changing the fiber radius with the coating density. Yes, fiber radius and the coating density. And we see some kind of very nice phases here that I'm going to discuss now. So there are four distinct phases you can see. When the protein density is very small, radius of the fiber is very small, they form this kind of elongated structures, not very well adhered and also not very like. Now if we go in this direction, we increase density but not the radius, then these proteins will, there are more proteins, then they will actually form like circular clusters, and since there are forces also, they will stretch in all directions and form this kind of green like structures that we also observe already in the flat surface case. Now if we go to the large radius, there will be competition between adhesion and bending energies. So this vesicle will, if the vesicle adhere, For larger radius, the addition energy gain will be larger than the bending energy cost. But for smaller radius, the bending energy cost will be larger if you try to adhere. So it doesn't adhere. So if we write the energies as a function of R and try to find out the optimum energy, then there will be some point above which the bending the addition energy will dominate. On the other hand, in this direction, the bending energy will dominate. And if bending energy dominates, it will not adhere because bending energy cost is much higher. And on the other hand, if addition energy dominates, it will perfectly adhere. Now, if you go again down, keeping the radius larger, we get another kind of structures where we have two arcs. They are stretching and form these kind of coil structures. They are, and this will actually explain our another experiment, that is the coiling of cellular protrusion on the fiber. And note that this phase, in this phase also the migrating vesicle coexists, that I already showed. Depending upon the values of F and E addition, it can have a migrating vesicle in the same region as well as this. And these are already studied in flat surface cases. Now you can see this movies. So depending upon these different parameter regime, either a arc can form or this kind of like structures can form. It can also have some simple analytical explanation of these like lines. For example, this is the phase where all the proteins form their ring-like clusters. So if we know the area of the vesicle, we will be able to calculate this perimeter and how many number of proteins is required to fill this perimeter will give us a line, analytical line that will quantify this transition. On the other hand, if we just calculate the addition and bending energies as a function of the radius and try to calculate the optimal radius, this will give me another line and that will quantify this. These are not exact, but qualitatively, these lines are actually qualitative. And similarly, you can also try to actually get this transition line. Now coming to the experiment that I already showed. So these experiments are already previously done, but the images on like these are called bright field imaging. They are not that promising, but these people repeated the same experiment on this case, which is called like 3D light sheet imaging. They are much more promising, much more like evident that these leading edges are indeed coiling and not just fluctuating in one side. So these experiments are done by these people. And again, the question that we asked before is that why these leading edges are going coiling rather than just going axially. And in simulation also, we can see that if we start from a two arc like shape along the axial direction, it will coil. And a similar mechanism can also explain this event.
So the experiment, what is the temperature? Room temperature?
Is room temperature. Yeah. So here also, if we measure different kind of energies, we'll see that we can explain this phenomenon by minimization of energy. And since I already explained the migrating vesicle, it is more easy to see because if we just consider this part and just forget about this other part, then what this small part is doing is very similar to what a whole migrating cell, migrating vesicle was doing in the previous case.
Possible to do a little more quantitative analysis of these dynamics? Because these movies that you were showing are very interesting.
Yes.
But I mean, how do I, for example, these dynamics that I'm seeing right now, how do I quantify it?
So it did not do
It
that.
is changing shape, the shape dynamics. Is it possible to measure some quantity then see how they are changing with time as it is undergoing these shape transitions?
Yes, it is possible. But we did not do this kind of analysis. It is interesting, of
This
course.
is a pure Monte Carlo, right?
Yes,
So how do you
Monte
get time information at all?
So yeah, time is not real time, but yeah, we can as for the Monte
There is
Carlo,
still
we can.
some
Yeah, of course, there's a dynamics, but you cannot extract from this kind of situation.
So
And multi-color, right? So how
you cannot compare with experiment with real time, but you can do some kind of.
so you have to no, it's a multi-color, right? But then it may not have anything to do with real time. It's not right.
No, I'm saying that just a quantitative understanding of, I see that something is just lacking.
See, that's what you may have already understood. Quantification is not possible. Yes.
I don't think it is not possible. No,
In
in that
multi-color,
measure,
you have the time information, right?
no, in that measure, how, for example, radius of dilation of this thing, how they fluctuate in each time.
Yeah, you can get the static quantities. You can get the fluctuation.
No, radius of dilation, I'm just keep saying radius of dilation as an example. How does it fluctuate with time? You can measure
To fix the time.
Yeah, measuring some quantity.
As I discussed, if I just consider this leading edge, this behavior of this part is very similar to the migrating vesicle that I described, and we can explain this phenomenon also by
This is Monte Carlo time, right?
yes, Monte Carlo time. Yes. And again, similar kind of explanation that explains this phenomenon also. And few other prediction that we did in the simulation is that if we make the fiber flat, elliptical, then there will be some kind of aspect ratio at which this coiling will stop, and they will try to actually just extend axially. In the circular case, if you measure the dynamics of this leading edge, we see that it actually is ballistic because it is rotating very persistently. On the other hand, in this case, if we track any such protein, we'll see that it is just doing diffusion kind of dynamics, and the alpha, this factor is 1 here. And now we try to actually understand this in the experiment also. So we are going to repeat this experiment on the flat ribbon. So what they did is they have 200 nanometer fiber, they cut in one part and then they to make it flat. And in the flat case, they observe very similar dynamics, that is fluctuating, not rotating. On the other hand, in the 200 nanometer case, they see that there are large like fluctuation, and very similar to our simulation. They observe like ballistic kind of motion in this fiber. On the flat case, they see diffusive dynamics.
So what is the role of temperature here? You come to it.
So, so I think it will increase fluctuations here. Yeah, in simulation, I can say that it will increase fluctuations. So we have to go to another parameter region. So everything will be valid. We just have to change those parameters, addition, force, and everything. They will be shifted in different temperature, but qualitatively they will be same. For example, if we make the temperature large, then we have to also increase addition strength in order to get similar results. And the last experiment that I'm going to show. So these people were doing this myelination experiment that I showed also in the beginning. So in the neuron cell there are some cylindrical part that is called axon, and some cells, swan cells, they form different layered structures on those cylindrical part. And these people are doing these experiments for a very long time, but they are interested in the long time myelination that takes 2 days. But they did not observe these initial stages, and when actually we asked them to actually observe the initial stages, they observed that in the beginning they did very similar dynamics that is actually observed for the previous cells on the cylindrical fibers. So they also rotate and they also coils. So these red parts are the axons. This green one is the leading edge of the cell. Cell body is somewhere outside. So this also shows similar phenomenon coiling around these axons. So at the end, what we did is that we actually propose a model of a minimal cell. So the cell with a minimal number of invariant that shows very similar features that is observed in real cells. We studied this migration of those vesicle on sinusoidal surfaces and also on fibers, and the conclusion is that they prefer concave surfaces on the cylinder, on the sinusoidal, and they actually go along the axis, and they don't prefer the convex one. And on the fiber also, when they are exposed to the fiber, cylindrical fiber, they prefer to go circumferentially and not along axial. And also, leading edge of the cell. So if we have two arcs, when we are exposed to the cylindrical surface, they prefer to coil and rather than going just extending axially. So this ultimately shows that there are some kind of like simple physical principle apart from detailed biochemical reactions that is there, and we can explain this. This is good for us because the thesis that not only we can explain this phenomena in detailed biochemical reactions, but using simple physical principle also, these kind of complicated behavior can be explained. So, and we'd like to thank all our external collaborators, NUPOP and other uh, groups. So the part of this work is divided into two parts. So this actually deals with the coiling of cellular protein around the fiber, and another part actually discusses the migration of vesicle and curved surfaces. And we'll summarize all these works starting from flat to phagocytosis to all these in a review. So that is probably some Journal of Cell Sciences, keeping in mind the biology audience that are going into much better details. And yeah, thank you all for your time attention.
Any questions? Could you hear from the back?
No.
You can leave it there. Any questions? Yes, we can.
So you were mentioning that they prefer the concave surface
Hmm.
and they try to move along that.
Hmm.
And when they pass to the concave to convex,
Hmm.
they do it at right angles.
Yes, yes.
So they prefer to go along the axis, and why they this kind of
Okay. So I saw that if the like region of the sinusoidal lobe is much larger, then it will get that much time to reorient, and it will indeed cross one maximum and then reorient on the convex region. But if the size of the substrate is very small, vesicle is much larger, then only it can cross because it doesn't have that much time to reorient. So it is very happy. It is thinking that it is going on a cylinder in the circumferential direction, very similar.
depends on the size of the cell.
Ratio of the size of vesicle and surface.
So one thing explains the inward movement of inside the cylinder.
Yes.
When it is moving axially, that
Yes.
explains why it is going and what happens inside of the cylinder.
Yes.
The bending is right angle.
Yes.
So, in the suppose the cell is in a flat surface, and if it is a protein, I mean, so I see that proteins sort of dictate the direction of motion,
Yes.
and so while it is migrating,
Hmm.
so there are when it is moving in a particular direction, so all the proteins are sort of clustered in the direction, and the other half of the cell is empty.
Yes.
So what is the interaction energy between the protein? Is it effective, or why it is always
Okay.
preferring the
So
direction?
the proteins are attractive, but this is not only the reason for the breaking of symmetry. Breaking of symmetry is coming from a very interesting thing, as I showed you, that the because of the presence of adhesion, some part of the actually vesicle will bend. That will promote the clustering of proteins because it will minimize the energy. Since there are more proteins, they will actually bend more. They will promote more proteins to cluster. In this way, they break the symmetry and form a leading edge. Even if we switch off the attractive interaction, this migrating vesicle can be opened.
And what is so, yeah. So what is the source? I mean, what is that ape? So ape is sort of dictating the direction of one. So this
Yeah,
force,
direction of yeah.
what is the source of that force? I mean, is it due to some sort of arising due to some sort of interaction, or
So the if I understand correctly, the source of the force is actin polymerization, The direction is in the normally outward. These are simplified emissions. In reality,
normally outward.
Normally outward of the principle.
How do you choose the value? I mean,
Value is a parameter. It can vary, and we keep, in this case, we keep the values in a region where we have migrating residents.
so if protein concentration is very small,
Mm.
then the cell won't migrate.
It will not. I think no, it is not true. Protein density, if it is much larger, they will form closed ring. It will not migrate. Small protein will always form cluster, and they will form migrating residents.
They will still there.
Yes,
Still,
yes, yes.
you randomly on the surface, some spread out the proteins.
Mm.
Do they try to cluster on one side? The dynamic dictating it.
Okay, so in the absence of addition, they will not do this. But in the presence of addition, there are some kind of positive feedback that actually allow them to migrate in clustering in one direction.
That would create a force field.
Yes, yes.
Any other questions? Yeah, I have a question. We were talking about this curvature axis, where proteins are following the curvature. But actually, there are some membrane proteins which follow the curvature, but they also change the local curvature of the membrane.
Yes.
It is known that.
Mm.
Now, in this case, you have only considered substrate whose curvature, etc., are fixed with time.
Yes.
They don't change their
Yes.
shape. What happens if you also allow that? Like
Mm.
large density of protein would also mean that they are bending the substrate itself, which actually happens in cell membrane.
Yes, you are right. So yeah, so there may be, I cannot say, but it is also into a future study. So yeah, this will become a bit complicated to say. Yeah, but it is interesting and it is realistic. One way to understand is the, like we can take one big vesicle, one small vesicle. This is the way, a simple way to understand. Yeah, that's possible.
So what should happen over rough surface?
Rough, it depends upon what kind of interaction you are imposing. Like by rough, you mean what will be the interaction?
No, I mean it could have different properties. So it's not necessarily sinusoid like this. It can have different kind of
Random.
curvature.
Random.
So positive, negative curvature.
Yeah, so it is also again not like
So
we
does it
said.
move at all? And it may not move at all.
So I think if it is very rough, depending upon the local region,
It can get trapped.
it can get either trapped or can get actually directed migration. Like if you can generate some kind of surfaces, it can also allow.
An experiment
Yeah.
on rough surface.
Mm.
Observe anything.
So one kind of, what I know is that one kind of surface is the two-dimensional sinusoidal,
Yeah.
where actually people observe that the cells are getting settled on the minimum or on the concave regions. This is what I know.
Could be some whatever saddle type of structure.
Yeah. But also,
Suppose the cell is large enough that it
Yes.
can fill the saddle. Maybe it's not possible to predict.
yeah, it's not possible to predict. But very interesting. Yeah, thanks.
Any other comments or questions? Okay, let's thank Rajkumar once more. I think there is tea, coffee outside, but I cannot wait.
কথা বলতে গিয়ে আমি আছি চলে আসতে হবে
আচ্ছা, ছোট শতাব্দী আছেন।
আমি আজকে 6:30টার দিকে চলে যাবো সাড়ে ছটা আগে
ঠিক আছে, আমি তাহলে
হ্যাঁ তুমি পারলে এসো
ঠিক আছে।
Nice result. Very interesting.